Okay, so let's look a little bit closer at the numbers that show up in our least squares regression line. Let's look at the slope first. And remember, in general, the slope of a line, it's that rise over run business. The rise, though, let's think of that as the change in y. And the run, let's think of that as change in x. So for example, if a line has slope 2/3, we know that if x increases, in other words, changes by 3 units, then y will increase by 2 units. Okay, so a change of 2 units for y corresponds to a change of 3 units for x. Or if a line has slope -4, so and remember, by the way, positive slopes, lines with positive slopes go uphill when you go along them from left to right. And just let's remind ourselves that a line with a negative slope is going to go downhill as you go from left to right. So if a line has slope -4, and let's rewrite that -4 as -4/1, we can see that if x increases by 1, so you go to the right 1 unit, the y is going to decrease. You're going downhill. Then y decreases by how much? By 4 units. So in the golfing example, the least squares regression line has slope. Where do you find slope in an equation of a line? Yeah, it's the number multiplying the x. So the slope 3.1661. Now let's think of that as 3.1661 over 1, because I need to have a fraction so that because I need to see that what's on top and what's down below, because I need to see change in y over change in x. So this slope tells us that if the club swing speed, I'll just call it swing speed, remember that's our x, so if that increases by 1, and these were measured in miles per hour, so if that increases by 1 mile per hour, the distance traveled right, because our y values represented distance traveled. The distance traveled increases by 3.1661, and distance was measured in yards. Now, one thing that we do need to add here to make this not sound quite so definite, remember this line is just an approximation of our data. It's what we think fits the data points best on average. So I can't say that the prediction is going to be exactly right. So the slope predicts that if the swing speed increases by 1 mile per hour, then the distance traveled is going to increase by 3.1661 yards. But I really need to say that it's predicting that that's what's going to happen on average. Okay, it's not an exact prediction. It's what we think will happen on average. Okay, and then the other number, so here's our least squares regression line model again. The other number in the equation of a line is this one over here. Remember, that's called that gives us the y-intercept. You might remember, maybe I should remind you of this version of the equation of a line. That's the format we've put our line into. Remember, the m is the slope, and then the constant term is the y-intercept. Okay, so let's talk about the y-intercept. And remember also that the y-intercept is where the line intersects the y-axis or the vertical axis. In other words, where x equals 0. Remember in algebra putting in x equals 0 to get the y-intercept? Okay, well, so to interpret that number, to interpret the value of y when x is equal to 0, we need to ask a couple of questions. First, is x equals 0 a reasonable value? Is 0 a reasonable value for, remember we called the x1 the explanatory variable, the one that explains the other variable. Okay, if it's not a reasonable value, then there's no point interpreting what you get if you put that value in. And then the second question is, do any observations near x equals 0 exist in the data set? Again, if the answer to either of these questions is no, then we will not try to interpret the y-intercept. The slope always has a meaning, but the y-intercept doesn't always have a good meaning. So in our golfing example, saying x equals 0, remember the x represented the swing speed of the club, saying x equals 0 miles per hour, it doesn't really make sense. Right, because, why is that? Well, because it would mean that the club isn't swinging. So, right, if the speed of the club swing is 0, the club is just sitting there, not swinging, because it means the club is not actually swinging. So if you're not swinging the club, you're not going to hit the ball. That doesn't make sense in terms of this situation. So we're just not going to try to interpret the y-intercept for this particular example. Now, so again, we said no to question 1, so we're not going to use x equals 0. But what about question 2? What's that business about asking ourselves, do any observations near x equals 0 exist in the data set? Well, in general, we should not use our regression model, in other words, that linear equation, to make predictions using values of the explanatory variable, in other words, the x, so values of the explanatory variable that are outside the scope of the model. Now, what do I mean by outside the scope of the model? Well, what we mean by that is meaning values that are much larger or smaller than those observed. And this is because the linear correlation may just not continue beyond the observed values. So yeah, the observed values give you dots that seem to sort of line up in a line, but if you go to the left or right of those, that trend may not hold up outside of there. So the point of question number 2, okay, the point of question number 2 that you ask yourself before you try to interpret the y-intercept, do any observations near x equals 0 exist in the data set? You're really asking yourself, is x equals 0 in the scope of the model? Okay, and any number that's not, any x value that's not in the scope of the model, you're not going to use with that model, with that equation. Okay, and again, just to get this terminology in the notes, this word model, when we use the word model in math or statistics, what we're talking about is an equation describing a real-world relationship. A real-world relation is called a model. Okay, and that's it for this section. So I'm going to stop the video there and come back and see you in the next one.